this past summer here. The summer, when I say summer, is the summer here in the Northern Hemisphere. So from May to August at the Air Force Research Laboratory in Wright-Patterson, Dayton, Ohio. And so I'm doing that because it to showcase the type of work that I'm doing most currently on one hand, and I hope it's going to also serve as a recruiting opportunity. So if some of the students attending would like to apply for a position here, for example, for graduate studies with me, this is the kind of activity that I plan to have a student working with me to do. So in this case, I went with a student. So the summer faculty program that they have at the Air Force allows you to bring a student with you for the program with the Air Force. So I wanted to then showcase the type of research that I'm currently working, and also if a student is interested, that we could also engage, and the kind of program that we could do. So we could perhaps then go to the Air Force over the summer to do some research. It's a great opportunity. It's really a great opportunity. They have great facilities, great folks, great people. You can have an idea of the cutting edge technology that what is being developed now in this area of aircraft design. Okay, so this is the idea here. The goal is really to develop a tool for aircraft design. And I have a very good friend of mine who is a designer with Lockheed Martin for over 20 years. So he has designed a number of aircrafts over these years. And in one project, he asked me this question. So he said, Marcelo, what we really need when you're doing optimization of aircrafts is to know where to put the next rib or the next spar or the next rib. Okay, ribs and spars are substructures of the wing. So that was the question he asked, and this research is, that I performed there, and with this title is really tailored towards answering that question. Okay, where to place the next member of the substructure. In reality, the question that I'm answering two questions actually. The first question is, do you need one extra member of that substructure? That's the first question. The second question is, if you do, where would be the best place for you to place this new spar or rib, or if you want a member of this substructure? Okay, so in that summer, actually, there were two goals, but they are related, and I can comment more on that later. So, but there are two goals. One was to develop a multi-scale design of a wing, and the other goal is really what I'm going to present or focus more today is the multi-fidelity topology optimization via two-point topological derivative for wing design. So just to provide you some context, in terms of the optimization, not only of structures, okay, but in general, you can divide, you can categorize them in three different classes. On the first one, you have the size optimization. Perhaps that's the simplest type of optimization. Okay, so we have an example there of a truss, and what you see on the right is the optimized solution. You just got the dimensions of the truss. In this case, the cross-section area. Okay, that's usually written as a linear programming problem. The second class of problems is shape optimization. If you see, you start there in the shape optimization with holes, right? But they are circles. And then the shape optimization can deform those shapes of those circles to something that is more high performing. Okay, and that's the solution on the right. And finally, we have topology optimization, which in a sense is the ultimate goal. The topology optimization asks a different question. It just asks where to place material in a certain domain. And so the main distinction between the shape and the topology optimization is that topology optimization allows you to create holes to destroy holes or to eliminate holes. If you see what you started with in the topology optimization on the left, you started with a blank slate if you want. So you just had a gray material there, and you ended up with the black one where you have holes. So it was able to create holes and choose where to place material. Okay, so in a sense, topology optimization is the end goal. And just for you to provide some, more rigorous context, topology, mathematically speaking, two objects are topologically equivalent if you can continuously deform one into the other. So if you see the shape there, that is a continuous deformation in one on the other. Now, creating holes in a domain is a discontinuous operation, and so that's the distinctive aspect of topology optimization. That's very important for many reasons. I will touch on some of them in this presentation. Okay, so let's start then with the multi-scale wing design, and I'm going to be brief here at this point because my focus is going to be the two-point topological derivative. But this is a method that I have been developing in collaboration with the Air Force for many years, and is based on the evolutionary developmental methods in biology. And I'm just going to go briefly here, and you have a reference here at the bottom of a paper that, if you are interested, you can see more details. The paper is of a relatively older version of the method, but I think it will give a good perspective what we have been doing for aircraft design. So basically, the idea here is we are going to try to find where to place things, how to develop a structure by mimicking the process that nature developed organisms, right? So nature developed organisms by a series of cellular division process, right? And that cellular division process is mediated, is regulated by the DNA. So the DNA, in that sense, can be seen as a program, right? A program written in this small alphabet, in this small language with the 4 letters, that when you execute that program, you develop the organism in a series of steps, cellular developmental steps. And this is what we do, basically. So we have a series of instructions that you can see here on the right that tells how to develop the structures in steps. So you see that the first step, it created a diagonal, then another diagonal, then create a square, and then finally it deleted the interior. So with a series of instructions, you can create topology. You change the rules, as you can see on the right, and they'll change the topology, change the layout. You can change the center, you can change the number, you can change completely different layouts. And so the method, the way we proceed here is we have programs that can develop structures in a series of steps, and then we evolve the program using natural selection, mutation, and crossover, the same way that nature developed evolve organism, or population of organisms, to evolve solutions for aircraft design, or for design in general, but in particular for aircraft design. So here's an example of applying that for aircraft design, and this is a single level baseline simulation, and this is a very realistic model of a wing. So this is a real wing that has been studied by Lockheed Martin in a multi-million project with the Air Force, and this is the same model that they are using, but they consider there are 9 trimmed maneuvers. In this particular example, we are just considering 2 because we want to just demonstrate the technology. Having 9 does not change anything, except it takes longer to calculate. And here's the baseline, has a mass of about 3,800 pounds. And here is how it looks like in 3 dimensions. So just the wing box, that's the focus of the design is in the wing box. So the center part here of the wing. So we also have the control surfaces there, and they are used for trimming of the airplane. But for design purposes, we are designing only the wing box. And then here is the design obtained with the methodology that I developed, the Tipo approach, and this reduces that mass by 20%. And that's is a major reduction in mass, so that you have an idea. The major aircraft manufacturers are really looking now into topology optimization. I have a current project with one of the aircraft manufacturers, and they are testing this using the most sophisticated, the most expensive software available. And in this project that I am collaborating with a friend with a much simpler problem than this one, at the moment, the tools that are available commercially for topology optimization cannot even equate to the baseline. So they are heavier. They are significantly heavier than the baseline. And we are able to reduce it by 20%. So this is, at the moment, this is the only tool that is capable of accomplishing this. And this design that we have is a design that is ready to be tested, if you want, or to go at least to the next stage in the detailed design. So this is in 3D, the representation of that wing box in 3D. And then now we are moving. So that was is a single level. So basically, it's the same model that they use. So you see here the webs on the substructure, right? So we have the spars. The spars is those that are going along the wing. So these are called spars. The ones going transversal to the wing, to the wingspan, are called ribs. And so So if you see here the webs, right? So the spars and what you're seeing here is the webs of the spars and ribs. So and the webs are made of shells. Okay, so these are shell elements. Now, what we are trying to do what we started doing in the summer was to move that to a multi-scale. So if you see here, the difference between this and the previous one, like this one, for example, is that now those substructure elements, they can also be they themselves can be trusses. Okay, so we can have trusses at a lower level, because if you look at the wing like this, so this is a supersonic wing. This is a 3% thickness wing, so it's 3% of the chord. So it's a relatively thin wing, and so what you have at the level of the substructure of the spars and ribs is a much smaller scale. And so that's the scale that we're putting now, trusses, as you can see here. And before we went for the wing, we did a test case with a box with a simple constant pressure over the whole wing. Well, it's just a box in this case, constant pressure over the box and a concentrated load at the tip, so that we will break symmetry. And here is just a result that we obtained. This is a relatively simple problem. And we got an improvement, but in this case, it was just 5%. But what is interesting is that so this is a reduction with respect to the best design that we found using spars and ribs, regular spars and ribs, and for the single level. Okay, so it's a 5% reduction over already an optimized single level structure. But what is interesting here is that we can have any layout, as you remember from the instructions, but the X layout was chosen. So of all layouts that it was possible, the actual X was chosen. And it makes sense, because the main purpose of having those members, right, spars and ribs, is to carry shear, and to carry shear the stress, to carry shear the X truss is a good design for carrying shear. And so, I don't have it here, but we actually started now calculations with the wing. So this wing here, we are now starting calculations with the same approach that we have for this multi-scale. So the multi-scale, the way we do is we have a nested set of instructions. So we have instructions to determine the first level, which is the layout that you can see from the top if you want. And then for each one of those members in that primary layout, we have the secondary level of instructions that it will generate then the layouts for the secondary structures. Okay, so that was what we did for the multi-scale. And as I said, at this moment, we put this to run, and we are waiting for the solution for this, for the full wing now. Okay, so now the 2-point topological derivative. This is the title of this talk. So this idea, this concept that I introduced recently, it comes to answer the question that my friend had asked. So where to place a spar or rib? Okay, but more generally, do I need to place do I need to include any new member or not? And if you do, where? Again, I'm going to present some results here, but if you want details, so I'll give a brief summary here of the method and some results. But if you want the more details, you can also check in this paper that is listed there. at the bottom. Okay, so basically that's the answer. The question we answer is, if you have a domain, the blue domain that you see there, and you have 2 points at the boundary of that domain, the question is, what would be the change that would occur in a certain functional calculated over the domain due to the addition of a ligament, a thin ligament connecting those 2 points, okay, connected 2 points P and Q. So if I add that thin ligament that you see in black there, connect P, Q, what would be the effect on the change of a functional? And if the functional is the compliance is a functional that is just twice the strain energy of the design, right? Which is the same as the work done by the external forces. Then you have this formula. So you can get a closed form solution in this form shown. So how does that work? Okay, so here's a validation first. So this is a comparison of the expression that I just shown here, this one, with the form. The thickness, you calculate the compliance, you subtract from the one without the ligament, and then you calculate that the topological derivative by just saying the change with and without divided by the thickness of that ligament. Okay, so if you do this and you compare with the expression that I showed you, you get an error, and this is the decay of the error. And you see that in the finite difference approach, it will be linear decay, and that's exactly what you see. So this validates the formula that I solved. And then, so how can I use that to do topology optimization? Well, that's one part that it connects to the cellular developmental process. I use a cellular developmental method here to develop the topology here, but now I use the 2-point topological derivative to answer the question where to add, if and where to add another member. Before I said, before I had a program that would develop that, and then I will evolve the program with the genetic algorithm. Here, no. Here, I'm developing just one individual, and every time at each stage, I'm using the 2-point topological derivative to either not to answer, not put anything, or if I put something, where to put it. So to illustrate it, I have a certain stage of the development. What I have then shown there on the top left, I have the frame skeleton. So underlying my structure, I will have a frame skeleton, okay, which is a graph. And then on top of that skeleton, I'm going to use a simple protocol that is just going to thicken those members and then get the Boolean union of them. And then I get the frame structure that you see on the right, top right. After that, I apply the finite element method to do the analysis. And when I have the analysis, I have the information I need to calculate the 2-point topological derivatives. And then I apply those 2-point topological derivatives to a set of candidates edges that you can see here on the bottom right, bottom left. And then I choose the best ones that you show on the bottom right to then affect the division. And you notice that it looks like one is missing on the triangle, that inverted triangle on the left. But the reason is that it's not that candidate's not there is because I can control manufacturing parameters to decide whether I want to add or not another member. And in that case, I had a minimum constraint on the angle that the new member can make with the existing members. And that's why you don't see one of the members there, because that would violate that constraint. So not only I develop a layout using that, information about where to place the members to best change the layout to minimize our goal, but we also can control manufacturability constraints at this level of the design, which is very, very difficult to do with the existing methods. So when I put these two together, and then after I add those two red bars, of course, it's going to change the stress distribution that was used to calculate the 2-point topological derivative. And so what I do is I perform a shape optimization on that, and that's what I got at the end. So if you think about it in this process of cellular division, I start with that blue on the top right, and then after cellular division, I end in the cellular dynamics to the shape optimization, I end up with the one on the right, the middle right. Okay, and you see here that I mean, when you put those red bars, of course, it creates banding on those bars that are connected to, and so the shape optimization, as you see, is a shape optimization to relieve the banding in those bars. Okay, so now how does that compare with existing methods, and how does it perform? So here's a comparison. SIMP is the most popular method available to do topology optimization, and it's the one that you have commercially available in, for example, Altair. Okay, and here is a comparison between our method and them. And as you can see, we do better than SIMP. So we can perform better than SIMP. And not only we can perform better. So the value that we're looking here, the objective function there is that JC. JC is for the compliance. Okay, and not only it performs better, but it's done in much faster fashion. Okay, and we can also do some things that so this is doing things in this is a classical benchmarks for this topology optimization methods, and this is this, but we can do the things that SIMP can do, and can do some other things that SIMP will have a hard time doing, which is for example, allowing the domain to be the full domain, the infinite domain. Because in many problems, you actually don't have a restriction on where to place material. You could place in any place, right? If you have a crane, for example, and so you don't to put this domain here in the SIMP. The SIMP method, what it does is it gets a domain, in this case a rectangle, and then it pixelates that domain, okay, and then tries to get the pixels in the right position. That's in a nutshell what SIMP does. But this has to define a priori a rectangle, in this case, a domain that is a rectangle. We don't have to do any of that. So we can have the full space. And if you allow the full space, there is a major gain in performance. And you can see here, it dropped from from 0.24, 0.18 to 0.32. So it's a major gain in performance. And for you to do that with SIMP would be much more cumbersome, because you have to do this using some sort of continuation method, where you have a certain domain, and then you enlarge the domain, and then you check if you can still enlarge more. So you have to do that in most steps, whereas I do this in most natural fashion. Okay, so that was a single fidelity model. Okay, so the model that we used here is a two-dimensional plane stress model for the finite element. And sorry, plane strain for finite element. But we have a skeleton, if you remember, right? We have a skeleton underlying that structure, that frame. So can we take advantage of that skeleton? And the answer is yes. So here's a result using now a multi-fidelity model and the optimization via the two-point topological derivative. We follow the procedure that I explained before, but instead of going to the frame, I do all of that directly into the skeleton. And in this lower fidelity model, because the skeleton lacks the thickness of the members, right, directly or geometrically, right? But you perform an optimization using beam models for them. So of course, beams have information about the shape and thickness of the bars, but they have that as attributes of those edges in the graph, rather than a geometrical thickness in the domain. And that's important because this allows us to use a beam model that is just one-dimensional, and is orders of magnitude cheaper than using a two-dimensional plane strain finite element model. Okay, orders of magnitude faster. Okay, so what's the idea? The idea is we use the lower fidelity model, the beam model, to run the optimization, to do the same cellular division and then shape optimization that I explained before. And then after that, we perform the shape optimization on the two-dimensional plane, plane strain model, to capture just changes in the joints. Because if you don't have the geometrical thickness, you will not capture the complex stress distributions that you have at the joints, right? Because the models, the usual assumptions that for beam models, for example, the Euler-Bernoulli assumptions that the cross sections remain unwarped and orthogonal to the directions. They are not true in general, especially close to these joints. Okay, so we can capture the joints there using the two-dimensional plane in our method that I explained before, but starting from the solution that we obtained from the lower fidelity with the skeleton. And what we get then is the result that you have on the top. It took only 75 iterations. After that, I did the same thing, but now using SIMP, which is that most popular method that I mentioned before, that basically gets a rectangle to be the design domain, and then pixelate that domain, and then tries to get the pixels. And I also use the level set method, another very popular. So these two methods are the most popular methods available nowadays in topology optimization, okay? SIMP on the left and level set on the right. The level set, as the name indicates, gets or models those the structure that you see on the right as the level set, the curves representing the level sets of a function. And then it optimizes the function, moves the function so that it gets the right level sets for the structure. But if you can see here, our method took only 75 iterations. And you know why? Because we have a much reduced number of design variables, okay? And we are using the multi-fidelity there as well in that case. Well, SIMP here, I'm using multi-fidelity for SIMP. So I use SIMP, the regular SIMP is in the top, is at the second row on the top line on the left. You have SIMP using single fidelity model. This is the regular SIMP if you want, okay? And I use two different resolutions because you see the effect of resolution on the solution. And then on that second row and then bottom row on the left, you have now these multi-fidelity SIMP. Okay, so I use the skeleton, I get the final layout, and then I start SIMP from there. And you see that you have gains already in SIMP of doing that. Okay, so I have better results, and I can do that in a slightly better number of iterations in this case as well. Level set, even more dramatic. The number of iterations reduction for using comparing our multi-fidelity compared to the regular level set is we reduce by half, less than half the number of iterations to conversions. So we have some of these results are shown in a preliminary paper that we have that has been shown in the aviation this summer, and we are finishing a journal paper on that that we want to submit soon. That is based on that paper. Okay, but we have can get some information about that conference paper already. All right, so now why SIMP? Why we don't do much better than SIMP? I mean, we can do better already in terms of performance, right? You see is 561 for SIMP compared to 551 for our multi-fidelity model. But look at the number of iterations. It's comparable. It's almost the same. And that's curious. And so that's why. I'm going to show here why. Okay? And here is the SIMP. Here's how SIMP goes. And SIMP basically already got the shape right. It's not now just going to move things around. But you barely can see any changes, right? The changes are basically almost moving at glacial pace. I have to accelerate it, as you can see now. If I accelerate it, it's just changing a little bit the position of this bar. There's no change in topology. There's no hole being created or any bar being eliminated. It's just moving a bar, but it takes forever for it to do it because SIMP, again, operates on the pixels of that domain. So it has to move thousands, tens of thousands of those pixels, and it can only do at the boundaries of those pixels. So it's an extremely slow process. Another thing that you see here is how SIMP creates new change topology. SIMP change topology, as you can see here, by creating holes. You can see here a hole on the bottom, the bar. Okay, a hole being created there. There is some gray material there where the hole is going to be created. And another gray area that you have here, more to the middle, where after you evolve, you see that they become then bifurcation structure. So SIMP creates a new topology by creating holes and then moving holes, compared to what we have here, where we created the topology in the low fidelity model, and then we are just changing shape basically here in SIMP. And that's the reason why we don't gain much for SIMP in this case in terms of number of iterations. because SIMP is a terrible shape optimizer, because it changes the shape by changing each individual pixel in the picture, which is a terrible way to do it. So here is, you see, this is changing, just minor change in the shape. Topology is completely right. It's just a minor change here, but it takes a long time for it to be able to do that. Okay, so we do better than SIMP. We can do better than level set, and we can do faster, not only better, but also faster than this method. So, okay, so that was for the benchmarks. Okay, so when you present a new method, you always have to go to the benchmarks, because these are the solutions that people understand. They know how to look at the results and evaluate the improvements that we get from those benchmarks. But what we really want is to do a design of the wing. That's what the Air Force is interested. That's what the manufacturers are interested. So to do that, I'm also using a multi-fidelity model now for the wing, and I have to also calculate a new 2-point topological derivative for the new configuration, right? The new setup. And the new setup is simply this. I have a plate, that domain omega there, and I want to know where should I place the next spar or rib, so the next reinforcement. That is done by the limit of that parallelepiped that you see there on top of the plate, when that cross-sectional area of dimension h goes to 0. Okay, so that's the topological derivative that I want to calculate, and this is fresh. It's fresh off the oven. Let's say we didn't submit this even for a conference yet, let alone a journal. Okay, so this was done over the summer, and so how we calculate that, so you have an idea. In this case, it's slightly different than the other one, because in the previous case, there was nothing that I had, and then I had to add something over the nothing. Here, I have a substrate. I have the plate. So the way I did is I calculate the shape derivative. This is that J prime, and then I can use that to calculate my shape derivative by taking the limit as h goes to 0 of this figure here, and choosing theta to be, theta here is the that you show here in this expression as well. This is the shape velocity for a certain change of parameter. Okay, so the parameter here that I'm changing is that h, and the shape velocity was the one that I showed before. So if you take the limit as h goes to 0, you get this expression. So this is then, for the compliance. So you're seeing here the compliance functional, okay, J of omega. You see here the equation of equilibrium for the elasticity, is linear elasticity, right? Small displacements. And then we have this. So if you have the derivative, the shape derivative is this. Now you take the limit as h goes to 0 for that theta that I showed before, and you get this limit as the 2-point topological derivative. So this is the closed form of the 2-point topological derivative, and that is the answer to the question that my friend had asked me, which is, where should I place the next spar or rib? Okay, so I did so with the star that we have at the bottom, I did a dimensional analysis of that 2-point topological derivative. I just normalized the variables with the length or stress variables, and then I obtained that in the bottom. Okay, and so what you see here is that the first two terms in the bracket, within bracket, I have the first term has a derivative of the normal component of the displacement at the solution, as a static solution, right? Multiplied by Gg is the stress. Okay, it's the traction that you have at the boundary. Okay, so there is no variation of U star in the N star direction. So think about that as dW dz in a thin plate. So that's 0. So that first term inside the bracket is 0. The second term will be important only when you have really large variations of the traction due to changes in the shape. For example, in the case where you have a constant traction over the layout, that term is 0. And that will be, in terms of wing, only really significant when you have, for example, shock wave boundary layer interaction, where minor changes in the shape around that area would create enormous change in the heat transfer and consequently the deformation. So, if you are looking at, hypersonic flows, that term close to the boundary layer, shock boundary layer interaction, that could be an important factor. Shock waves, even in supersonic flows, I don't think that might lead to major changes. So, okay, so that's the second term. The third term inside the brackets, you have the work done by the body forces, and that involves a fruit number squared, calculated with the sound speed of in the metal, which is extremely large, right? So about 5,000 meters per second in steel. So it's a very large number. So this means that the work done by body forces usually will not contribute much, which leads then to the answer to my friend's question, which is, where should you place the next spar, the next rib? Well, in the line that, when you calculate the strain energy along the line, gives the largest strain energy. So that's the answer that this equation provides, okay? Try to reinforce the lines where you have the largest amount of strain energy. That's what it means. Okay, so I have a preliminary result that I obtained over the summer with this, but before that I had to do a validation, as I did for the two-dimensional case. And then I faced a very interesting problem that I was not expecting to be a terrible issue initially, which is, when I did the validation for the two-dimensional case, let me show quickly here. When I did this validation, this mesh that you have here on the left had about 1 million degrees of freedom, okay? So the finite element had over 1,200 million degrees, 1.2 million degrees of freedom. So when you go to 3D, well, 1 million in 2D corresponds to 1 billion in 3D. And so then it starts to get complicated. So I tried to do first with the adaptive method, the same adaptive method that I had used with the 2D case, and it was not satisfactory. I started running out of memory very quickly. And I tested 2 finite element methods, could not do, because I need high precision for this. So what I did is, and to have an idea why you're seeing here the strain energy at the top surface, you see this kind of regions of very high gradients in the middle of the plate, the side of the plate, that have to be resolved for you to calculate properly, to get enough resolution to calculate the topology derivatives. So I could not do that with the regular finite element method, so I developed a Galerkin method via Legendre polynomial. So it's a spectral Galerkin. So you see here the 2 families, actually there are 4, but the other 2 families that are shown are basically variations of the families on the right. We just shift on the first mode. And Legendre polynomials, they're great because they are orthogonal, right? With respect to the to the weight 1, right? And so I can apply this directly to the equations of the weak form of the Galerkin method. And so that's what you have there, the bilinear form. This is the standard finite element method. So, but I'm replace now my discretized or my function, my approximate function, right, with the finite expansion with respect to that to the tensor products of those Legendre polynomials. I put that in the weak formulation, and I obtain the usual stiffness equation KU equal B. All right. So, but so I did a verification of the code. So I used the method of manufacturer solutions for that, and here is the error that you obtain. So you can see here the spectral Galerkin shows the usual exponential decay in the error. So look at the error, how it drops, right? 10 to negative 1, 3, 8, 14. So at 64, 64, 16, I already am in machine accuracy. Whereas the usual Galerkin is still dropping at polynomial rate, so it's much slower. So it's still 10 to negative 4. And for what I really need, the compliance, you can clearly see here the speed up that you get. So as I said, with 64, 64, 16, in the spectral Galerkin, I already am at machine accuracy. So if you look at the compliance that is calculated, that's what I want to calculate for my validation. I have all figures that you see there are correct. I have the approximate value of the exact compliance is just because I have to truncate, right? You in general have an infinite number of tail numbers there. But if you look there, you see that I have all numbers already correct with the compliance in 64, 64, 16, whereas the usual Galerkin method with using a Lagrange P2 finite element, I still only have the up to the third decimal place correct. And I need 6 decimal places to do the validation. And so that's why I developed this spectral Galerkin. And then here is now for the validation case. We see that we have convergence for our case. The finite element and usual finite element does not. And I have to mention one thing is that with this methodology, I can actually, with the spectral Galerkin, I can actually impose exact symmetry conditions, whereas in the Galerkin method, usually you have to apply them using penalty techniques. And that was important for me to get the accuracy that I needed. So I applied the symmetry conditions, which reduced by 4 the number of degrees of freedom that I can calculate, that I have to calculate for this spectral Galerkin. And so this just to show the sparseness. So you see that it's sparse, and when you apply this, the symmetry you get on the right, so it's still sparse, but it's a different pattern for this is the sparseness pattern for the matrices. And why we need this spectral method here? We can look at the spectrum of the stiffness matrix, and you see that you have a large variation, of course, as usual in the spectrum, of course, of useful calculated modes. And here you see why we need really to go spectral. The red is cutting in with 3 decimal places, which is usually satisfactory for engineering applications. But if you really want to do a high accuracy, if you need high accuracy as I need here, I have to go to the green bar. And now you see in the contributing modes to the strain energy spectrum, you see that if I only need 10 to negative 3, I just need 4 modes. And you see that the 4 modes cut very close already to a very low wave number. So I can get away with a finite element method, regular finite element method. But if I need 10 to negative 6, I need 127 modes, and I need a much higher wave number that is shown here on the left of that spectrum. So that's why I really need to go to the spectrum. And then if you do that, now I still have to do one thing, because that was all spectrum for one member, but actually I need to put one on top of the other. So for that, I develop a graph method that uses the spectral in each one of those members, and then use transfer of the information in the different nodes of the graph. And the transfer of information is traction from, in this case, from the top, from the ligament to the skin, and then I project displacement from the skin into the ligament. Now, the projection of the traction is immediate, because the traction enters the weak form of the equations with the inner product, and is immediately available. Now, the displacement, on the other hand, I need to calculate the actual displacement and project that. And so that does not enter directly with the inner product. So I had to do, so we have to project first using the inner product, but then you have to remember that what you obtain are the covariant components of the vector. So you have to do a raising index to get the contravariant. But if you do that, then you obtain the right result. And here's a comparison for verification with the standard finite element. It agrees well. And finally, we can do the validation. Here's how it behaves when you decrease the thickness, which should be a quadratic variation, is using a Taylor expansion, and you can see you start to appreciate the quadratic when you start refining the mesh. So I have validated. So to conclude then the presentation, here's a preliminary result of using this for wing design. And we had 2 levels of fidelity for this case, a lower level of fidelity where you show here, which is just beams and plates. So you have in each panel that you see there, you have actually a plate, okay? But it's a flat plate, so it's a 2-dimensional model, okay? Pure 2-dimensional model. And I play 2 load cases, and I have constraints on stress. It's the L6 stress norm. I also had constraints on minimum length, minimum angle, and boundary belonging, so that I keep the geometry, the fidelity of the geometry. And then here are the optimized lower fidelity on the right, and then the optimized higher fidelity on the wing. That now with the same model that we used for the original wing that we started the presentation with. Okay, so this is still a preliminary result. We are very satisfied, pleased with the preliminary results. So we, as I said, we can still reduce the mass, whereas the methods that are available in the literature or commercially, they cannot. But I need to do more cycles here, more studies, but we are pleased with this initial result. So just to sum up the main accomplishments, we are starting now the multi-scale wing design. We have finished the box design, and we developed this multi-fidelity cell developmental method first for frame design that is both faster and more effective than the traditional methods. And now we are very encouraged by the first results that we obtained applying that or extending that for wing design. And that's what I have, folks. So thank you.
Thank you, Professor. Thank you for your talk. That was a great talk. Please, guys, if you have any questions for Professor Kobayashi, you can send it using the chat or raising your hands. Or we already have Yuri. Professor Yuri, please do your question for our friend Kobayashi.
Hello there. Can you hear me?
Yes, I can.
Hello, Marcelo. Nice to meet you. An excellent talk. Thank you very much.
Oh, thank you.
It was great. So I have probably a very naive, simple question. When you presented the 2-point optimization, and not only the 2-point, but all the optimizations that you presented here, given that you are talking about an aeronautical optimization in which you really need to perform at the highest level, right?
Right.
Have you performed any sort of unicity studies on your minimization processes? Are there other solutions that you can probably achieve based on initial conditions, initial guesses that you input to your model that can be equivalent or perform or have a lower mass with a higher stiffness or something like that? So is there have you performed a study on the unicity of the solutions of your optimized solution?
Oh, that's an excellent question. Thank you very much for asking, Yuri. So the answer is there is no mathematical proof for even mildly complex problems like the benchmarks problems that I'm showing here. I don't know if you can all see.
Yep.
Right. So even for this well-known benchmark cases, you can see the variety of solutions that you obtain by changing parameters in the simulation. One parameter that you mentioned that is very important is the initial point. So just before I proceed, so to answer your question, there is no mathematical proof of uniqueness and of a method that will give you the global optimum. There is no method that guarantees you that you get the global optimum. No method. And that's number one. Number two is that there are a multitude of optimal or local optimized solutions, and that can vary depending on many factors. I'm showing some of them here. On the SIMP side, you see there just changing the resolution. So if you have the second row here, you have that SFM. SFM is single fidelity model. So SFM SIMP that you have on the second row, top left, that is obtained with the 800 by 200 fidelity. And then you have the next tweet on the right, one that is the same method, SIMP, same conditions, same initial conditions, but a different resolution, 1600 by 400. So I double resolution each direction, and look at totally different result, right? So changing the resolution, not the initial condition, already changes the solution. Now, changing the initial condition, as you can see now comparing to our multi-fidelity, you also change the solution. That's what we have right underneath the one that I mentioned that has a number of iterations, 990. So changing the initial condition dramatically changes the solution as well. And if you go to level set, look at the different solutions as well. I didn't enter many details here. There are lots of things to be said. So I have to project, well, actually I have to embed those initial solutions that I obtained with the lower fidelity into the higher fidelity model. And so this is what you see here, the embedded layouts first, and then what you get at the end. But you see that changing the initial conditions dramatically affects the performance of the solution, the efficiency of the method. So yes, so there is no uniqueness, and they can change dramatically. The only thing we can propose is a method that gets optimized solutions. And we are getting optimized solutions that perform better than the ones that are available out there. And one reason is because we have way less number of design variables. And I can't comment on that, but perhaps if somebody is interested in another question. But you see here that another thing that is interesting is that you can see here, you can have some different layouts, but with very similar values of the functional. It's to say that if you look at the space of different topologies, it seems that the optimal can also be flat. So not only you have no uniqueness, but you can also have flatness in terms of different layout spaces that you are, or of topology space that you are, that can be very close to the optimal value. So does it answer your question, Yudi? It's not. It's definitely not a naive question at all. It's a very important question. I appreciate it. Yeah.
Thank you. So Taiguara, if I can have a follow-up question.
Of course, please.
Yeah. Thank you. So Marcelo, yeah, definitely that answers the question. And my question was actually motivated on the mathematical grounds that eventually that you can probably find a variety, a subspace of the space where you define your the functions that are solutions that minimize your functional, that have a constraint. And maybe by projecting on that functional and minimizing over a reduced space, a reduced dimension space, you can probably find a better minimum with added constraints. Is that possible?
Well, I understand your point. Like, for example, if you want to minimize or maximize perimeter, right? Of course, if you don't put any constraints, there is no solution, right?
That's right, yes.
Yeah, so if you put a constraint on the smoothness of the perimeter, then you get solutions. But no, I understand entirely your point. But of course, and in a sense, that's what the intent of SIMP. But even SIMP will have multiple solutions. So for example, SIMP here, if you don't filter, so SIMP uses a filter. And I should mention here, problems like trusses, this is not really a truss, this is a frame, but because it can carry bending. But as the volume fraction is reduced, this approximates a truss. Now, there is a well-known result from Michel from 1904, where if you have a domain like this and a problem like this, and you try to put a truss on that, there is no solution. So, I mean, there is a solution, but there's no solution in a sense, because that solution has an infinite number of members. So, which basically tells you that if you can if you add more members, you can also get a little a real reduction in your functional. So there is no actual solution because you can keep reducing. It's like the fractal solutions, right? And so SIMP, to avoid that, put constraints exactly as you mentioned, right? And use filters to reduce the space and get solutions. And that's why you get those solutions. But still, even in that reduced space, you can see you have multiple optima. And for realistic problems like this one here, I see very little hope that we can ever get, for example, a reduced space where we have a convex problem. Of course, if you can reduce so much that we get a convex problem, then you have uniqueness. But I doubt that. Well, at least in the near future. I cannot be pessimistic to say ever. But in the foreseeable future, mathematically, is very hard. I mean, the equations that you have to solve for this kind of problem, they have all partial differential equations. They're just too complicated to be able to write them and determine spaces where you can get. I don't know. Maybe I'm being a little bit too pessimistic. But that would be a very interesting problem to look at, Yuri. Absolutely.
Excellent. Thank you.
If you can carve
very
out
much,
some subspace, that would be very interesting already.
Yeah, I see. Thank you very much. Very, very nice talk. Thank you.
Okay, thank you very much.
Thank you, Yuri. Any more questions? So, Marcelo, I have a question. I'm sure my question is naive. So, you show an application for aeronautic wing,
Right.
But do you think we can just apply like that your technique to optimize structures in wind turbine blades? Because a wind turbine is pretty much like an aircraft wing, but you must give it a twist in order to find the correct attack angle for each position in the radium, right?
Right.
So do you think we can use the 2-point topological optimization or something like that to strengthen and get the blades, the wind turbine blades lighter, and maybe we can also optimize the shape?
Well, first of all, thank you very much, Tigar. That's a great question again. I mean, if you say this question are naive, then my answers are naive too, because it's the same level. Well, so the answer is absolutely yes. Actually, that has always been one of my interests. Is when I present this, many people ask, "Can you apply this to cars?" The answer is yes. Can you apply it to ships? Yeah. So it can be applied. This is a general approach to topology optimization. So it can be applied to engineered structures, even fluids as well. Could be pipe networks, for example, things like that, or heat transfer. Yes. So the answer is yes, it can be applied. Now, can you do shape? Absolutely. That's a very interesting question, actually, because working with industry, I wanted to do, so in the paper that I have here, let me see this paper.
Because in those applications you show to us, the shape is a constant, right?
Yeah, but look here, topology, shape, size, control, surface.
Okay,
so in this case here, we did everything. We did shape optimization, we did topology optimization, we did
Nice.
multi-objective optimization. So that was, the objectives there were two, were minimization of mass and maximization of L over D, right? So lift over drag. So we had two objectives there. And the shape affects tremendously, of course, the lift, all aerodynamic properties, right? Lift, drag.
Oh, okay.
And so there was a strong coupling between structural part and the aerodynamics there. So yes, absolutely we can. But the interesting thing is, when working with the manufacturer, he said, let us do first without changing the shape.
Okay.
Because what he wants to learn first is what's the gain that you obtain just with changing the layout, just the topology, keeping the shape but changing the layout. And so that's what he wanted to do, and because what he wants to gain is insight. You know, we cannot go to these companies, you know, people who have brilliant people working there forever designing aircraft and say, okay, now we are presenting this tool here that's going to do everything that you know how to do, right? That doesn't make any sense. But we can tell them that this is a tool that can help them improve their designs. And so what they want to gain from this exercise is to understand how they can improve their own conceptualization of the design. Can they learn something new? So, you know, this is very preliminary, but you know, you're getting a reinforcement, clear reinforcement here of the brake. So if you have a double trapezoid wing like this, what can we learn in terms of designing this? Where to place the spars and ribs? Makes sense, Taekwondo. So he wants to know, he told me, I want you to explain to me what's the function of each one of the spars and ribs that you have there. And so for that reason that we do not do shape, because he wants understanding before we get to the actual result.
Okay, I see.
But that's a great question. So the answer is yes, and I would love to collaborate on that area, as well. I have been working on this mainly because I have been being funded by the Air Force. Yeah, and we did some in satellites as well, because we got funding for satellites. Yeah.
So just one more very fast question. I have a problem when where I simulate a droplet, and there is a computational mesh, a computational grid around the droplet, precisely in the interface. Sometimes the droplet gets so distorted that I must add some points there, and if I just populate and get the mesh more and more refined, in some point I must decide how to reconnect the elements, you know?
Right.
So, but this must be a very fast operation, because I'm doing that on the fly. You see, during the simulation. Do you think that from the theory you are working on, I can get some wisdom to do my job fast, or to make better decisions on my algorithms to how to reconnect the dots in my computational mesh?
Yeah, excellent question, Taiguara. So in reality, I have to face a similar problem, as you can tell, going from this layout to this layout, right? Look at this layout here and this. So the mesh, I have to do something with the mesh. And so doing remeshing so I have, basically, to answer your question, what I do is I use a combination of two approaches. I use a remeshing with some automated capabilities. I use Gmesh, and Gmesh is a nice tool, because it allows you to, you have the challenge many times is to automate all of that, but you have this available in Gmesh that you can tell, you have special points where you want to add to refine more the mesh there around them and things like that, right? And so I can do a remesh, but doing a remesh can be very expensive, as you mentioned, right?
Yes.
So what I do then, I before I do a remesh, I first calculate a moving mesh using a barycentric approach. I don't know if I have it here to show you. Let me see. Where do I have that? Let me see.
Like you just move the dots, the points.
Well, yeah, you know, the finite element has barycentric barycentric coordinates, right, for triangles.
Yes.
Now there is a generalization of that notion for any polygon, convex or non-convex. And that generalization is actually used for wrapping images in computer graphics. And so I use that here. So it's a very simple algebraic operation, but that keeps the quality of the mesh pretty reasonably well.
Nice.
For my interest, at least, it worked very, very well. So it's very fast. I compared the barycentric against the usual moving meshing techniques that you use in ALE, right? Because your problem probably, I'm sure you're using an ALE method, or there is one way at least that you can use an ALE method to track the boundary and move the mesh. And so the usual techniques for you tracking the mesh or moving the mesh in ALE, like the Winslow, right, or the Laplace or the elasticity, I program them and compare them. They are just too expensive, as you mentioned, even to move the mesh.
Yes.
This is algebraic and keeps a really good quality of the mesh.
Because we have several methods that you must to solve a PDA problem.
Exactly.
To find the new mesh. And we just want something faster.
Exactly. The Winslow method is a non-linear equation to solve, right?
Yes.
And it's very, and it's very sensitive to the initial conditions and all of the stuff. And so, absolutely. And so I tested and compared with the Winslow, and we got, for the test that I made, I got comparable meshes. And if you have convex to convex, there's no problem. If you have convex to non-convex, is where you start to get problems, right? But you can perhaps create barrier regions, so you can split the domain in domains that are convex, and then you just apply them in the domain, the convex domains, and then in the convex domains, the barycentric moves very well the mesh points.
Okay, very nice.
So then what I do is I do a barycentric first and test the quality of the mesh. I use two parameters. I use aspect ratio aspect ratio and angle, minimum and maximum angle. So if the quality of the mesh is acceptable, I continue with the one that I did, the barycentric. If the quality of the mesh is not acceptable, then I remesh.
Okay.
But if you remesh, you have to be careful in my case. But if you're doing CFD, remeshing might be actually more easier to do because you can just project and continue from there, right?
Right, right. So, any more questions to Professor Kobayashi? Well, in that way, I would like to say thank you again, Professor. That was a great talk and our great pleasure to have you here with us. And thanks a lot. I hope to see you soon.
Me too, Taiguara, me too. You are always welcome here.
Okay, thank you.
Thank you, everyone.
I think I have one more question, Marcelo. Don't leave my hook yet. I have a question from Professor Alini. From a dynamic point of view, do you evaluate natural frequencies throughout the optimization process? Depending on the application, this may play an important role. Is this a concern for you?
Excellent question. I mean, I really appreciate all the questions. So yes, for example, for the wing here, well, in this case here, this wing design here, we actually have flutter constraints on this. So flutter is an instability of the wing. If you have seen the videos of that Tacoma Bridge in Washington State, you may remember how it started oscillating and then collapsed. And so it's called flutter phenomenon, and is an instability, a terrible instability for the wing. So, and the way you model it is you have a reduced model of the dynamics of the wing using modes of the wing. And so in that case, we calculate the eigenmodes, and then we reduce the dynamics using those eigenmodes, and we solve then the stability issue in that reduced model. Now, we did that here, and for this one, we had to actually use didn't have to, but we used a bootstrap method that was to accelerate the process, where we did not have the flutter, because as you mentioned, Aline, very well, I mean, if you add eigen problems to the solution, they can be expensive, they can be finicky. So to improve the efficiency, we first performed it without flutter. We get a solution without flutter, and then we start a full solution, including everything that we calculated and flutter, that starts with the solution that we obtained without flutter. So we had to do that in 2 steps to in a sense address the issue that you're asking, to make it more efficient and more stable. But when you do all of that, then you get optimized solutions that satisfy flutter constraints as well, in this case. And just a short comment is that what it basically did was, it did not really change the mass, the actual mass of the wing much, but it moves the mass towards the leading edge. That's a well-known phenomenon. So flutter in wings usually is when you have an interaction between the first bending moment and the first torsion moment. And the usual remedy is that engineers know and use this to move mass towards the leading edge to avoid that amplification of the oscillation if they're out of phase. So so if you do this, so then the optimizer found that out by itself. But the interesting thing is that it was just a redistribution of mass without really much change in the actual value of the mass. But yeah, so to answer the question, it is a concern, and there are ways that we have to work to work around that. There are lots of other details that, of course, I don't have time to discuss here, but I would be more than happy to talk offline with anyone who would be interested. Thank you for the question, Aline. Yeah.
Thank you, Marcelo. Aline says thank you too by using the chat. So thanks again, and till the next time.
Till the next time. Okay, thank you very
Bye-bye.
much, everyone. Bye-bye.
Thanks, everybody.
Bye.
Bye-bye.